In the last video, we talked about those different formats we have in sequence data. And in this video, we're going to talk about how to work with data, how to bring the data set and convert them into different formats to work with. And in the earlier video, we showed there's a data set called actual. And this is a function we use to take a glimpse of the data set actual, which describes 2,000 different people, how their states or statuses have shifted in 12 months during a year. All right, so this is the structure of the data as we have been talking about. And to create a state sequence object, as I mentioned earlier, we can just use this function, sequence def, provide the data, and then provide the variables we want from the data set. Remember we used, first we used the column ID or column number. And here we can also provide the column names or variable names to pull those columns into this. Just want to show you there are different ways to kind of provide the parameters for this function. And it's achieving the same thing as the earlier function, which creates a sequence object. And here the output information tells you there are 4 different sequences, 4 different states. There's a coding of the state, there are 2,000 sequences. The max and minimum length of the sequences are the same because this data is well formatted. Because this data is well formatted, it's really clean and it's smaller. It has 2,000 sequences. And I imagine as you work with digital learning data, you might bump into much larger data set, much more messy data set, and could be data set with some missing values, could be data set that have different kind of that are not aligned perfectly in terms of, in this data set, you have everybody start from this month and end in this month. But in a real world data set from digital learning, you might have different learners starting at different time, right? So there's a lot of messiness as we think about the temporal information we capture in those digital learning platforms. So as we started with this clean data set, and I want to also, maybe we can play with the messier log file, or log file that maybe it will better represent what we can encounter in a digital learning setting, right? So in this example, I'm pulling this example from a research project I'm part of, involving multiple teams that is interested in examining playful problem solving. And this project is situated in a commercial game. It's a puzzle game called Baba Is You. The game is a puzzle game. It provides a player an environment to define rules in this micro environment. And the players is in charge of manipulating and sometimes destroying the rules, sometimes creating new rules, so that they can achieve the winning state of the game. And the data set we're going to play with is a tiny subset of the data set we have for the project. It comes from one particular level of the game. It has 180 or so players who have played the game and who has used a special version for research that tracks their playing process of the game, right? So, but I want to show you how this game looks like. And this is the video, not from our participant, but from a YouTube creators who publish their own process of playing this level. And the level name is called Where Do I Go? So let's take a quick look at the level and how this game looks like. So you see the players controlling this character who is called Baba, and the players broke this rule. War is stop. because if the rule is active, right? In the beginning, this rule is active. This player cannot get through the wall. So this player realized they have to break this rule. So that's what they did here. They broke this rule so that it can actually move across the wall right now. And the player is pushing other text boxes. Now they created a new rule that's called flag is win. In this case, if this rule is active, you see the player is moving towards the flag and then achieve the winning state. So this player has conquered this level by creating a winning state and then achieving that winning state. And as you see, this is a puzzle game. It could be pretty simple from this example, but in later levels, this can be very complicated because there are more game mechanics introduced, different kind of rules and possibilities introduced. It can get pretty complicated. It will be not as straightforward as this level. But anyway, we have this log data again from this level, from 180 or so players playing this level. And the data set is coming from level 1 logs.csv. It's a already well-formatted data set from our original log data. Our original log data is much more complex, but we have researchers cleaning that data, wrangling that data, and then putting that in a format. We're going to read the data first. We're using the read CSV, and then we're going to format that as a data frame. And here's the first 20 rows of this table. And if you look at this table, you see the first column's ID, the second's begin, and then end, and then state. Right from the get-go, you might notice this is the spell format of this game, of this sequence data set, right? Because every row has an ID, which is the ID of the player, has a state, which is a state of a particular status in the gameplay, and then there's a begin and end. That's the action or the state, and when that begin and when that ends. And then I want to mention that the number here for begin and end, they're in the seconds. So that's from 1 second to 1 second it started, and then you see there's a pause, right, for the first sequence. After they started, they paused for almost 5 seconds, and then the player started moving, right? It moved the key, which is up and down, right and left, from the 5th second to the 11th seconds. That led to removing a rule. And then this player started moving again for another around 45 seconds. And then this created a new rule. And then they moved their key again and then got the winning state, right? So this is the end of the game because this could occur, the key press that moved the character Baba into a flag, for example, and then that achieved the winning state of that level, right? So this is a pretty short sequence of a gameplay session that provides you pretty detailed information about the process. And the same apply for this next sequence, which is a different player, which has different kind of process in terms of how they played, and they also win the level. Right, so this is only the first 20 rows. And I believe, okay, this CSV file has 3,000 rows that has, describes the sequence data in this spell format. But the real, the original data set is even messier, as I mentioned. Just because our analysis here is only for the sequential analysis, we already cleaned the data from the original data. But original data looks something like this. It's even more complicated because you have the index of the action, the ID of the player, the session timestamp, the level timestamp, because when the players play the session, they might play different levels. And you see this level timestamp start from 0 versus session timestamp could be a different value. And there are other, other objects, such as we're tracking the rule set, the rules that are active, the level that have been completed already by the player, and so on. So, we really, again, spend a lot of time to go from the original data set. I would mention that the raw data set is even more complicated than this one. But we went from the raw data set to this data set you see here, from this level. And then for this analysis of sequences, we even further cleaned this up to this format to be analyzed, right? The good news is after all that kind of work, we're now, we have this clean data set that represent a play session or many play sessions by those players, which has this clean spell format. And we're ready to analyze. But before we do any kind of analysis, I want to also mention there are a lot of decisions we can make as we are first getting started with this. Let's put this kind of BABA situation up to the side. But if you're using the data set that's from your project, you might first ask questions like this. What is a sequence in my data, right? For this data set, it's pretty straightforward because it's a sequence of player behaviors, right? It's very straightforward, but in some other cases, it can be messy, can be not as clear-cut in terms of how you define a sequence. And, as I mentioned here, each sequence could be a player, or could be a session, or a sequence could be an attempt, right? The player could be playing a level multiple times, even in this data set, right? Do we separate those attempts into different sequences, or do we keep them together because it's consecutive actions by the same player, right? There's still some decision to be made. Another question we ask is about the granularity of our analysis. Again, there's no direct answer to this. What is the time unit in our data? Is it every second, every minute, every 5 minutes, every hour, every week, right? There's always something that's, can be debated. And this is where the theories can come in. This could be where the learning context matters as well, or the learning design that matters, that will shape how how different learners perform in this context, that will shape how you choose the time unit, right? It's important to ask those questions as you get started with the project before you do even any kind of exploratory analysis, right? The good news for us is we have that data, again, as I mentioned earlier, in the spell format, and let's import that into TriMiner. And since the data is clean, so the next step of creating that TriMiner object, sequence object, is straightforward. We convert that to this data frame. We feed that data into, again, this function. You should be familiar with this function already. We provide the data, the name. We provide the variables we want. There's some additional configuration we have here, which is basically this override. This is important because sometimes TriMiner will not like to have two different states occurring for a particular time period, right? So they will try to overwrite, right? If I have win and keystroke together in a particular time, TriMiner might decide to throw one out. And I don't want that to happen because for me, for this project, it's important to keep them. So I have this override set to false. Those details, again, you can read the help menu, help information from those function by calling question mark followed by the name of the function to read more about those details. But here we are going to use this function to, convert the data to an object. And then outcome is here. It will tell you some basic information about this object. It has this many, the time axis, which stands for the length of the time. And there's 9 different states in the data set, right? There's end, idle, key press. That means the player pressing the key. It could be up and down, left and right, and then restart the level, adding a rule, removing a rule, start the game or start the level, undo. Sometimes the player can rewind, can undo their behavior, the actions, and then win. And there are 184 sequences in the data set. And here it's more interesting than the first example. The sequence, the length of it, it could be the minimum is 12. That means a quick win or quick quit. It depends on what that sequence is. And there's the maximum sequence is 3,600 seconds, right? So that's a long sequence in this case. But with this information, we already have some basic understanding about the nature of the data in terms of how many sequences, max and minimal sequence length, the number of states, and you will notice there's some void elements and missing values, which are coded using those symbols. Again, in this kind of exploratory sequence analysis, it's usually a good idea to take a look at the first few sequences, right? So we can call the first 6 sequences using head function. We'll return the first 6. The first one, start and then followed by, again, this stands for missing value. That means there's nothing that happened during those seconds. And then followed by key press going on for a number of seconds, and then led to a rule remove and keeps going. And then this is a long sequence actually that ends with a win, right? So this is how the sequence would look like if you put this out and print this out to the RStudio. And we can also print out the sequences using different formats. Right. Remember, we have many different formats. This is a bit too busy. And this is the original. This is the STS format. We want to maybe use SPS format that's more condensed. And here, in the start, that there's a pause or a missing value for 3 seconds, and followed by those different actions, which provides a different view of the data. And similarly, we can plot the sequences using the same function we used before. Let's plot the first 10 sequences from the data, and we can keep the legend, set the legend to true. We can set a title of this figure or this plot to be index plot, the first 10 sequences. And here's a visual of the same data we saw earlier. Here's the first sequence looks like this. There's the legend of the colors, and the second, third, and so on. And here I want to mention that we limited the length of the sequence to 100. Just because if you don't do that, remember the longest sequence in the data set is 3,600 or so, right? It's a long sequence. You might want to set up a value to limit the length of the sequence to focus on the more interesting parts and to not let the outliers make this visualization unreadable. And you can play with different numbers for this configuration, but the idea is you want to set up the length of the sequence to be a smaller value than the max. Right, with that, I think we have achieved the goal of importing this more messy data set from a project and put that in our trial miner, created a sequence object, visualized the first few sequences. And again, this is something that will need a lot of thinking, and there are a lot of decisions that you can make in the process. I want to remind us we can ask a number of questions as we're dealing with this process, such as what is the state, what is the event, what is the sequence in my study, what is the time granularity of my sequence, right? Those questions matters a lot for this kind of sequential analysis, and answering this question will need not only knowledge about the analysis, but also knowledge of the domain, theories of learning, and theories of gameplay in some cases to make informed decisions. So I'm looking forward to learning from you about how you think about your decisions in the process, because mine is limited by my own knowledge, my own domain, and your decision will be different than mine. And finally, for this video, there's a bonus segment of this video, which deals with the gaps, the missing values, and so on that might occur in the sequences. Here, I would just want to be a little bit brief for this topic, because this information is provided in the slides. For those of you who are interested in learning more about this, you can take a look at the slide and play with the code yourself. But basically, TriMiner provides you a way to deal with either missing values. In your sequence, there might be missing values from the beginning, or it would be missing value considered by TriMiner. Remember, in the gameplay data, there's some segments or some time period the player didn't do anything, right? It's a pause. It's pretty natural for me as a researcher, but TriMiner think there's missing value there. So TriMiner provides you different ways to manipulate those different values or possibilities, right? So this additional information is provided here for you to play with in case this is something you care about in your project. And with that, I want to, let me scroll down to the end of this. Yeah, with that, I want to thank you for your attention. And in the next video, we're going to talk about more about some statistic analysis of sequences.